This is a recording of my first patron AMA. I get a lot of good questions and had some great conversations with my live audience. If you'd like to join these AMA sessions in the future, you can sponsor Inductica on Patreon for as little as $5 a month. $5 donors will get exclusive lectures. $30 donors will receive a copy of my theory of induction, the theory that guides all of our research here at Inductica. So let's see my answers to questions on physics and epistemology here on Inductica. Welcome everyone to the first Inductica Patron AMA. I'm very honored that all of you have decided to support Inductica monetarily, and so I wanted to give you all this privilege to ask me your questions, to be part of this exclusive meeting. Again, I'm very honored that you all have chosen to support me financially, because you didn't have to do it, of course, and you could have gotten the value I produce for free, but you all have decided to support my project, and that really does mean a lot to me. So as part of Value for Value, I'm going to try to be doing a lot more of these. And so let me tell you how our structure today is going to work. I have a bunch of your written questions. I've selected some of the written questions I received. I only selected some of your written questions that I'm going to go through in a first segment. Okay. Any of the written questions that I sent back to you in an email, you can feel free to just ask in the latter half of the meeting, where it's just going to be a free-form conversation, or where we're going to be taking live questions. For this first meeting, it actually won't be so much of a free form. I want to keep things on a track as much as possible. And sometimes when we just kind of let the conversation go wherever everyone feels like it doesn't stay on track. So I'm going to be a little strict in this first one, but we'll see where it goes, and we might loosen things up as we go. So now, when I take a particular person's question, we can definitely, that person should unmute, and then we'll have a back and forth with that person. So the first person I'll take a question from is Bruce, because Bruce is the biggest contributor to Inductica. So I wanted to honor him with, more than his share of questions, because he's, dedicated more than his share of the money here. So I really, and Bruce, I really appreciate it. Like we met at an objectivist conference in Greece, and you overheard me talking about my theory of induction to someone on the bus, and you said, "Wow, that really sounds great. Like, do you publish your work?" And then you watched all my videos or something that night or something, right?
As much as that, well, it wouldn't have been possible that night.
Right. Well, I didn't have that many videos back then. That was I had 6 videos back then, and that was it. But
well,
I mean,
17, your series of your induction of physics series that you've moved.
Right. Okay. Yeah, that would have been tough to watch that in one night. That's 34 hours. But
yeah.
Real quick, everyone, I'm seeing a lot of laggy. Am I laggy for you guys? Okay. It looks funny, but everything's recording just fine, probably. Okay. So I'll take one of Bruce's questions first. So Bruce asked, I have a curiosity about what happens inside of a black hole's Schwarzschild radius in light of Dirac proposal that photons are the carriers of force. Unless I'm missing something, this would seem to imply that no acceleration is possible inside the Schwarzschild radius, meaning that the velocity of any masses just inside the radius can't differ from their velocity when they reach the center, assuming they ever reach the center. Would it also consequently mean that the internal structure of a black hole cannot rotate? Would rotation not require acceleration towards the center? Yes, it would. Rotation does require acceleration towards the center. So this is a good question. As an activity of the ether, does the black hole represent a situation of the ether's capacity with respect to Represent a saturation. Oh, okay, situation. A saturation of the ether's capacity with respect to mass and force. That I'll answer the last one first. That is an interesting hypothesis. It's like the ether has maybe been deformed so much that it can't be deformed anymore or something like that. And that's what you mean by a saturation. Yeah. There's two ways. Well, that's certainly intuitive. Hey, we start without you, Mr. Memes of Destruction. Thanks for joining us. I forgot.
I apologize. Better late than never, I guess.
Yeah. You've only missed the reading of the first question. So basically, Bruce's first question was, would an object, once it's inside of a black hole, would it be unable to accelerate more towards the center because it's already going the speed of light? Okay. And at least wouldn't that follow from what Dialect was saying about Dialect's proposal as to why an object cannot go faster than the speed of light? Well, so let's see. So you're basically saying like the radial velocity of the towards the center velocity of the object is already the speed of light once you reach the Schwarzschild radius. So, isn't it the case that it couldn't speed up in that direction? Let's see. Well, here's the thing. If this also kind of presumes I'm not sure how to look at this other than to think about this as the same way as the river model, the idea that a black hole is sucking ether in from every direction. And so let me try sharing my screen here. And hopefully this doesn't make my computer explode. So we're already a little resource intensive here. Let's say this center point is where all the mass of the black hole is, and then this black circle is the Schwarzschild radius. Let's see. So you're saying some object. If it's at the Schwarzschild radius, you're saying like basically the ether is already at this location moving at the speed of light. So isn't it the case that the guy's already moving with respect to the ether at the speed of light, so he couldn't go any faster than he's already going? Well, here's the thing. At this point, he's already moving pretty fast. Not at sea. He's already moving fairly fast to begin with, so he isn't already moving. He's not moving at speed c with respect to the ether. Now
he's shy of speed c, yeah.
Yeah, he's less than speed c as with respect to the ether. So as a result, an object could still accelerate radially under this logic. I mean, there's other things that might be going on that we just don't understand here, but based on the logic we understand so far, he could still accelerate radially. So let's actually draw a spaceship here. Once a spaceship is in here, so here's a childishly drawn spaceship. Let's zoom in. Here's a childishly drawn spaceship. Its velocity is already something. So, I mean, it can still accelerate towards the center, and that would lead to a particular orbital radius. This kind of reasoning has also, like Chantal said, that in certain media, there are actually optical black holes that because the density of, like, say, glass gets a lot larger in certain areas, what will actually happen is light will go in. Let's have a blue light beam. Light will go in, but then because of the refractive index, it'll spiral in and then it'll never come out. So it's not like a mass black hole. It's not a gravitational black hole. It's an optical black hole. And so the light comes in and then it just spirals around. And then at a certain point, it reaches a radius where, and you can calculate this with simple geometry of what that radius would have to be based on the mass of the black hole. So it could be the case that it's not that the black hole is some kind of place where, you know, anything that special happens. It could just be the case that the black hole is just a place where light happens to spiral around inside and it never comes out, and so it's black. No light comes out. We don't know what's going on inside of a black hole because once anything goes in, it doesn't come out. So it could be that this is all that's happening. It's just that the light is going around in circles. That's all very speculative, though. But this is what these are the speculations we can make based on what we know so far. So any follow-ups or anything on that?
No, I'm trying to recover my other thinking when I wrote the question. I'm not being successful at the moment, but there was something along the lines of crossing the Schwarzschild radius would imply that, and this is where I think I might have gone wrong, is that light can't travel between objects inside that Schwarzschild radius, and therefore it could not impart force.
Yeah, I'd have to think about why that is, but if we make the ether velocity purple here, remember that, like, I think a really key thing that you may have been missing when thinking about this is that the object is already moved, at least under this ether flow hypothesis. If you do other hypotheses, I'm not sure what you'd come out to.
So it's inertial motion with respect to the ether.
Yeah, it can still go. I mean, it's not yet going the speed of light with respect to the ether. So, yeah. And I forgot about the hand raising feature, which Rick is using. So go ahead. What do you have? What you have a question there, Rick?
I want to state. I want to say that part of the answer needs to be we don't really know.
Yes.
And that really is important here. That any of this is, when you say wild speculation, it's really more rooted in we don't really know than anything else.
It's rooted in a particular hypothesis, but and we can reason from that hypothesis. But yes, it's important when doing so to emphasize the we don't know part, because otherwise it makes it sound like I do know, which I don't. But this is what follows from my understanding of that hypothesis. I'll move on to Bruce's second question. Here's the question: would a sliding platform on slippery ice full of rotating bike wheels in complementary rotations, ensuring that the systematic angular momentum is zero, require more translational force to move than when the wheels are not rotating? Okay, so let me draw a picture of this, of what he's talking about. Okay, so here's some ice, here's a platform, and we're gonna have a bunch of wheels. Okay, and so we're gonna have one wheel rotating such that its angular momentum points up. So it's rotating that way. And then we have another wheel rotating the opposite direction. Yep, and so its angular momentum is down. Basically, if you don't know what angular momentum is, we got one wheel rotating one way, one wheel rotating the other way. And what if we had a bunch of such wheels so that all their rotations kind of cancel out to zero? So there isn't any total angular momentum. Would that be harder to move? And the answer is no, it wouldn't. It doesn't take any extra force to like translate like these bits of angular momentum, these objects. It doesn't take extra force just because they're rotating. I like where you're going with this though, because there is a model of inertia where they model inertia, and I think Dialect's video on, I've seen this a few times, so I can't remember where I've seen it and where I haven't seen it, but I think Dialect's video talks about this, where it models a photon, it models the inertia of an object as being caused by a photon bouncing back and forth inside of a box. And if you think of the photon not as having mass, but as having momentum, and photons do have momentum. They can, and what the hell does it mean for a photon to have momentum? Because it doesn't have mass, so what are you talking about? part of what it means for a photon to have momentum is that it can cause a change in motion of masses. So it can cause momentum in other masses. So we attribute momentum to it. Dialect also has dialect does have an argument, which is very reasonable, for why we should think of the photon as having mass. It requires a reconceptualization of what mass is, though. Not that that's a problem, but anyway, getting back to this, we can model inertia as being caused by a bunch of photons bouncing back and forth inside the box. And it turns out when you think of the photon as bouncing back and forth inside the box, the difficulty in changing the motion of this entire thing gets larger. In other words, the inertia, the difficulty of changing its motion, that becomes larger when there's a photon in the box bouncing back and forth. So, Bruce, what you're saying here kind of reminds me of that, only it's a rotational thing. As you might know, if there's only one rotating thing, I brought my yo-yo, which is my favorite rotating thing. If this yo-yo's spinning, strange effects happen when you try to twist its direction of rotation. And I bet that's why you had all the bicycle wheels canceling out. I can't help but demonstrate one of my favorite effects, which is precession. So I'll throw the yo-yo, and then I'll put my finger into it here. Let's see. Yeah, there we go. Okay, watch. The yo-yo turns. The yo-yo turns because what I'm doing is it's spinning, and I have my finger stuck in it here. Now, normally the yo-yo would twist like this, but because of a combination of how torque affects angular momentum, it won't tilt over. Instead, the direction of rotation turns. It keeps turning around like this. So part of what, Bruce, you were doing is avoiding that, right?
Yes.
Yeah.
Yeah, I was trying to come up with a macro model for thinking about translational inertia, figuring if the units are actually composed of rotating things, and that's the source of it, maybe we could look at it.
I want to point out. I want to point out a philosophic flaw in your thinking here, though, which is in this model, we're modeling inertia in terms of the momentum of a photon. We're modeling inertia in terms of not inertia. But what you're trying to do in this bicycle example, I think, is it's like you're modeling inertia with more inertia, basically. Like, why is it that it would be difficult to change the motion of this thing? Well, it's because of its inertia. So let's see. Like, you're asking, you're kind of, the motivation for this question, I take it to be, you're making this hypothesis, maybe the reason things have mass is because they're rotating. But
to a certain extent, that makes sense.
To a certain, so so I don't know, maybe you're not so much making this error, but it's an important error to point out one way or another, which is like, if the object, so if you're making the hypothesis, like maybe the object has inertia because its parts are rotating. Well, why do rotating objects have inertia? Well, it's the same reason mass has inertia. So it's like you're explaining a thing with like the same thing on the lower level. It's what Terence Deacon calls a homuncular argument, and this comes from the idea of is people used to ask, like, why is man conscious? Like, why does the body have motion and everything? And one very silly answer that was given long ago was like, because there's like a little man inside your brain. Well, but you're saying, well, why are men men? It's like, oh, well, because there's a little man inside the brain. Well, is there a little man inside the little man's brain? Like, is there mass within mass? Is there mass within mass within? So it's like, we got to watch out for that kind of that kind of thing.
Watch out for the argument.
Yeah. Matt, what was your question?
Oh, I didn't. I was just because when you were describing that inertial thing, that made me think of two quick things. Is I actually remember seeing somebody take like a power drill and like a magnet, and then they had another piece of like metal and stuff up there, and it's literally just doing the thing. Like you can see there's air, there's distance between it, but it's literally using that electromagnetic rotation to help lock something into place, which then made me think of when you were talking about the photon in the box for inertia there. Does it necessarily need to be in a box, or could it be in some standing wave? Hypothetically,
Yes.
of course, because
Yes,
I know John G. Williams.
Actually, yeah, that's a good point. Yeah, that's a good point. So the box I drew earlier is just it's just a simplification, really, of like it could be that instead. Let me show the drawing screen. All right. By the way, are the drawings choppy when they come up, or do you see them?
It's actually pretty good. I actually kind of like the functionality here.
Yeah. It comes from my tutoring. It's funny because in tutoring it's GoodNotes. Notability has been a real problem lately. Anyway, the idea is that, you know, one hypothesis I've heard, and again, it's really important to note this is a hypothesis, is that electrons actually constitute light moving around in circles. And if this were the case, then basically you could get all of this stuff happening, or I'm sorry, you could get all of the effect of this model from a view that electrons are moving back and forth. Each of these electrons is really is light moving back and forth, and that light moving back and forth in a standing wave, in a circular standing wave, is causing the same basic effect as this. That if you want to move that standing wave across, there's inertia. Why? Because it's difficult to get that standing wave to get it to change its behavior. So yeah, that's a good connection there. Yeah, cool. Okay, so let's move on to someone else's question. Okay, this is a question from a longtime fan of the show. I promised him, he's not here, but I promised him I'd answer his question, and I finally am. So Hans asks, what do you think about the pilot wave theory by de Broglie and Bohm? Are there any flaws from, let's see, is there any flaw in this interpretation of quantum mechanics? The most accepted is the Copenhagen interpretation, which is deeply wrong. Yes, the Copenhagen interpretation is just, it's off. It's not worthy of consideration. Other than the fact that like it makes correct predictions, but it needs to be replaced. So the de Broglie-Bohm picture is basically the hypothesis that instead of it being a particle and a wave at the same time, it's a wave pushing a particle around. And basically, I think this is a very reasonable hypothesis. It could be right. However, there is a alternative to this, which I think is more, it ties more things together, and that is not proof on its own, but it does make it a hypothesis that I favor more, which is the following. The hypothesis I favor more is that that there really aren't particles. If by particles we mean small entities, what there really are is just waves, and the appearance of particles is really the result of the ways that the waves interact with one another. That's the hypothesis that I favor. All of the evidence that points to particles could be accounted for by the fact that waves have to be absorbed in certain discrete amounts. Now, why do waves have to be absorbed in only discrete amounts? It's because of the phenomenon of resonance. So in the in the atom, there are only certain energy levels that the electron can reach. And the reason for this is because the electron, at least in part, is a wave phenomenon, and those waves can only resonate at certain frequencies. Okay, and to understand this in common sense terms, think of a musical instrument. So I'll pick my favorite, which is the cello. So the cello has strings. The strings can only vibrate at certain frequencies because those are the only frequencies that will fit on the strings, basically. I can go into why only certain frequencies fit, but I'll skip that for now. By placing your hand on the strings, you're shortening the length of the string, and then it accommodates different frequencies. So the idea is that the ether around an atom has a certain set of frequencies it can accommodate, and that is why there are only particular energy levels. And it may be that this is the cause of why particles, well, maybe I shouldn't call them particles, of why these entities, these wave-like entities, we know they have a wave-like property because of these quantum effects. Because of these, maybe these wave-like entities have a discrete amount of mass, a discrete amount of charge, and discrete amounts of energy, simply because those are the quantities that they are allowed to be emitted and absorbed in. Because these wave phenomena can only be absorbed and emitted in particular discrete amounts because they are resonant waves. That is the alternate hypothesis. But yeah, the idea that it's particles getting pushed around by waves, that's pretty reasonable too. It seems like this other hypothesis seems to be consistent with more of the facts though. Okay, so Matt, go ahead. What are you thinking?
No, I didn't even know.
You have your hand up.
I just never lowered my hand.
Just keeping that hand up. Okay. All right. Now let's move on to Adam. One of your questions you sent me, Adam Lohr. How does your approach to the scientific method differ or overlap with approaches by others such as Karl Popper, Thomas Kuhn, and Francis Bacon? So I'll start with my favorite. I'm heavily influenced by Francis Bacon. I did a whole video on him. He's, let me think. Behind Ayn Rand, he's my biggest source of inspiration. Well, not just inspiration, but just of ideology on this issue. Bacon brought humanity into the inductive method. Before that, it was a lot of like wild speculation, basically. Science was consisted of a lot of wild speculation, and he emphasized observation, induction, and having a systematic method. And he developed that systematic method, and a lot of his theory of induction can be found in my theory of induction. Parts of my theory of induction are just either I've taken from him, only small parts I've straight up taken from him, and then I wrote so in the book, and other parts are augmentations of what he has written. And if you've ever heard of Mills methods, so like the method of difference, the method of agreement, I rename those Bacon's methods in my book because in Bacon's treatise, he goes through a process that's very much like Mills methods, but broader in scope. And so it doesn't just cover like before and after situations. It covers any time that one nature is associated with another nature. In other words, when that's his terminology, when one set of characteristics or properties tends to coincide with another, he has these ways of identifying logical linkages. I shouldn't say logical. He has ways of identifying proper physical associations between these characteristics. I call these conditioning connections in my treatise, but he has ways of identifying these connections, what are commonly called cause and effect relationships, but they're broader than just cause and effect relationships. And he has a whole way of identifying those. So a lot of the great scientists read Bacon's work over and over again, and I recommend any scientist today do the same. I've done so. Okay, moving on to the bad guys now. Popper. I'll do Popper first. Popper is the champion of the hypothetico-deductive method, which is, it's the standard scientific method we were taught in school. The idea that you guess, check, and revise. You come up with a theory, you have the theory make predictions, you do an experiment, and if the theory if the theory makes the correct predictions, then what? Then you're a little more confident in your hypothesis, maybe. But people who advocate for this rightly say that it never proves the hypothesis. Now, I want to say something else about this, which is I think to a large degree, it is responsible for our current predicament in science, our current impoverished state in physics. Not in all the sciences, I don't think, but definitely in physics. That's what I know. I couldn't speak to the other fields. But because of the hypothetico-deductive method, think of the corrosive effect this has on the core of science. With the hypothetico-deductive method, you pretty much only know, did my theory work or not? Did it make correct predictions or not? So what ends up happening is you start, if that's your only standard for what a good theory constitutes, then what ends up happening is you don't end up really caring about the truth. You only care about whether the theory got the correct predictions. And as a result, it becomes completely secondary whether you think the theory correctly identifies the actual nature of the underlying phenomena. You become unconcerned with this because, number one, a lot of people just don't think you can do that anyway. There's a lot of skepticism in science right now. But number two, if this is, even if you're not a skeptic, if this is your guiding light, if this is what determines good science versus bad science, then why bother getting the answer right when you have an answer that works? Why bother identifying the actual nature of things when you don't have a way of knowing the actual nature of things? You only have a way of knowing if you're getting correct predictions. And this is why I'm strongly in favor of bringing back inference. I think this is inference, like making deductions from the known facts to dig deeper into what is observed. You make observations, but you don't just look at reality and that's it. You make the observations and then you make inferences from those observations in order to penetrate past where your senses can identify. And I specifically, by the way, for the objectivists in the audience, I specifically use the word deduction here because some of the literature in objectivism has kind of scared people away from deduction. And all of that literature is completely correct because deduction is very easy to abuse, but I don't want people to become racist against deduction. Deduction is very important. So I want to emphasize the places where it has its proper place and call it what it is, deduction. So, okay, now finally, Thomas Kuhn. Kuhn has a theory of how scientific revolutions come about, and his theory it just misses the idea that there's a such thing as objective truth. It misses the idea that scientists can try to be objective. The theory basically states that science is it's a social trend. Any given science is basically a social trend. And, you know, when evidence starts to contradict that social trend, the new scientists will start advocating for a new science, and the old scientists will entrench and will not allow new opinions in. And you basically have to wait for the old people to die. And he has this whole theory of how scientific revolutions happen. I don't have a lot to say about it. It might accurately describe the social happenings of a bunch of scientists who fail to be true scientists. It might accurately describe that. I don't know. I haven't spent a lot of time thinking about that. A lot of times these skeptics, they'll say a lot of stuff that's actually really true about how people behave when they're not being rational. But it is possible to be rational and objective. You need the right scientific method. You need discipline to adhere to it. But it is possible to be rational and objective. When you see evidence against your theory, you don't have to just reject it. You can be objective and say, "Oops, I was wrong." So I think that's very corrosive to the scientific process, where he just doesn't think people can exercise, intellectual honesty. Basically, I think that's very corrosive. Now, Adam, I'm interested. This is a little bit of a sidetrack, but I'm really interested to know Give me your background. Where are you coming? What's your background, and what got you really interested in these questions in philosophy of science?
So I'm actually an artist, and I've always been very interested in math and science and physics and stuff over the years. And until more recently, like I just wasn't really trying to pursue it seriously. But I, the more and more like I'm learning about it, and I have my own kind of theory, and it keeps kind of coming up with things that seem to be pretty accurate that I didn't know was a standard thing. So I've started to really take it more seriously, but yeah, I largely agree with everything you're saying about the difference between Kuhn and Popper and Bacon. Like I think Thomas Kuhn's. I was really surprised. I thought Thomas Kuhn was writing a scathing critique of how terrible our society has become. He's not. He's saying this is normal science.
Yeah,
Epicycles is normal science. That's just what science is. Like that's not science. Like I don't know. I
I
I
think
was very
epicycles
surprised.
can be science, by the way. It depends on how you take them. But yeah, like the idea that you can, but the idea that, it's that there's really no difference between epicycles and what replaced it. It's just a
Sure,
social
yeah.
convention.
Yeah.
Yeah, it's very like the moral decay that causes is, I mean, we're suffering from it. I mean, we're suffering from it in a lot of ways, but I'll stick to science for now. If scientists don't think it's possible to be objective, like they'll behave this way, because
Right.
why would you not? If you don't think it's possible to nut up and do the right thing, then why would you exercise the difficult discipline of doing that? It's hard to admit you're wrong. You need some moral guidance in saying, yeah, this is possible, and it will pay off if you admit you're wrong. But instead, you get this guy basically saying, nah, people just don't do that. And
Yeah.
it's moral decay. It really is. Well, I appreciate that, Adam, well, I'm glad you're thinking about philosophy of science. That's really great.
Awesome. Yeah. Yeah.
Yeah.
Thanks for the opportunity.
So, okay, so I'll take Essa's question now. The density points you presented are now okay. So he's referring to my video on my fluid hypothesis of the ether. Okay, fluid hypothesis of the ether. The density points you presented are now points of positive charge. Points of negative charge would behave the opposite way. Yeah, that's right. I mean, so yeah, whenever there's a place in the ether that has more compaction, that behaves as a positive charge. Whenever there's a place in the ether with less compaction, it's a negative charge. That's what's going on in the fluid hypothesis in that last video. When it comes to the phase field, and what he's specifically talking about is the phase field of an electron, the inner waviness of an electron, which is affected by the A field. Basically, the A field that I present in that video changes the inner phase of an electron. When it comes to the phase field, it contains information not only about the 3D oscillation of phase motion, but also about the oscillation of an observer's own time projection, i.e. in the fourth dimension. Now, I'll give commentary on this. So what I'll be doing here is giving this is a rather long comment or question, and whether it's a comment, I forget if it amounts to a comment or a question. This was a comment on one of my YouTube videos that Essa posted, and I wanted to, whether it's a comment or question, I want to comment on the parts. So you're saying that the inner oscillation inside the electron is not just a 3D oscillation. It's not just an oscillation in 3 dimensions, but it's also an oscillation in an observer's own time projection in a 4th dimension. So 2 things I want to say here. First, I don't think we can make time into a 4th dimension like space. I've mentioned this in other videos. Time is a result of the fact of change. And I think it's really easy especially because relativity does this, it's easy to treat it as a dimension that's just like space, basically, and it's interchangeable with space. But if you look at the basic nature of time, that is not the nature of time. Time is a result of the fact that things change. And so for example, can you go back in time? Well, no, you can't. So what would that constitute? What would it mean to go back in time? Let's say go back to World War II. What it would mean to go back in time is like you'd have to change everything back to the way it was in World War II. You'd have to rearrange molecules and have Hitler again. You'd have to rearrange molecules and have Eisenhower again. If that's even possible, you'd have to do all of that. Well, you didn't go backwards. If anything, you went forwards. I mean, you didn't go forwards either, because time isn't like a spatial dimension you could go backwards and forwards in. You changed stuff until it was the way it was back then. So so time is. I think we need to one of the biggest things we need to do is change the way we think about time.
Yes.
Yeah.
Yes.
Okay. Awesome. I'm glad I'm getting agreement on that. Okay, so I'll continue. So that's just my comment. I'll continue reading. So it's an oscillation in a fourth dimension, as it says. As if alternating forward and backward in time, but for an observer moving at nearly the speed of light, that same oscillation is mainly an oscillation in space. So this sounds very much like the standard relativistic view. I'm sure you have a view that differs from relativity as we progress, but so far this is in agreement with relativity. And the idea is that if an object is moving very close to the speed of light, the way relativity thinks of it is it's moving through space but not moving through time. One way I used to think about it when I was young, when I was trying to like understand this stuff, was I thought, okay, if an object is stationary, it's moving through time at the speed of light. And that is like the normal speed at which it moves, at which an object moves through time. I didn't understand this about time back then. But when an object moves through space, it's moving through time slower, and the total speed is always the speed of light. So if it starts moving through space, since the total speed is the speed of light, it has to move through time more slowly. And so that's where he's coming from. And again, you can see like this kind of intuition is really necessary to, I don't know if it's necessary, there might be other ways to think about it, but this intuition is very compatible with special relativity, but you can see it turns space into it turns time into a dimension of space, which there's no evidence that that's the way it works. There's all the evidence is that time is a fact about change. Okay, so Essa goes on. In my own phi BSU theory, I have explained that 4D ether, I've explained the 4D ether precisely, and it turns out that charges that are opposite to each other do not interact with one another because they reside in tachyonic sectors with respect to one another, i.e. at superluminal speeds with respect to one another. Their own mutual causality is opposite to the causality of the other charge sector. An imaginary observer built solely from charges of the same sign would model an oppositely charged object as moving continuously in its course of time towards the past. Okay, now the reason I wanted to comment on one of the biggest reasons I wanted to comment on this is because I receive a lot of emails and comments like this, and I want to give everyone advice on presenting their scientific ideas, because I don't want to say you're wrong, because I don't know, because I'm not sure what you're saying. And so I wanted I want that my main comment on this is that in these comments, and I get a lot of these, so I'm not just picking on you, Essa. I'm trying to give you some advice for explaining the theory. You need, when explaining your theory, you have to ask, who's my audience? What do they know? And what do I need to explain to them that they don't yet know? So for example, even as a physicist of 17 or so years, I don't know what a tachyonic sector is. Okay, like most physicists don't know what that is. You've come up with this idea, or maybe it's an idea that's out there, but if it's out there, it's very niche and esoteric, and it's not of general knowledge. So if you want me to understand what you're saying, you're going to have to explain what a tachyonic sector is, and you're going to have to explain it in terms that I already understand. So identifying some more things. An imaginary observer built solely from charges of the same sign would model an oppositely charged object. So then you get into some way of explaining it. You're trying to say that, like, I guess if an object has a bunch of oppositely charged signs, then it'll interact with everything else oppositely. I don't necessarily, I mean, I'm not sure what the theory is, so I can't really say if that's, but I think that's really all I want to say here is, like, I think I'll not read the rest of it. I know that might be really disappointing for you, that like I didn't want to read the whole question, but that's really because I've already lost you. And so that's why I don't want to read the whole thing, but I wanted to take this opportunity to help you communicate your ideas. Because and the number one thing, once again, is think about who you're talking to, what they know, what they don't know, and how can I explain my idea in terms of things they already know. And I'll just say, like, reading this whole thing, a lot of this, it didn't connect with me because I didn't understand a lot of your assumptions. I didn't understand some of the terms. And so to explain it, you really got to think of how to break it down. And I'll tell you, it's not easy. Chances are the thing you were trying to communicate can't be communicated in a single paragraph. So you have to just become less ambitious if you're writing a YouTube comment. If you want to make a whole video on this thing you're talking about, then, maybe a 20 to 50 minute video, then you probably could explain all of this, but you got to do it in an order that allows someone uninitiated in your theory to know what you're saying. You have to explain it in terms of stuff they understand. So I get a lot, by the way, I get so many emails from people explaining their theory to me, and this is what happens a lot of the time. So if I'm ignoring you, that's what, a lot of times that's why, is because it might just be that I disagree. I'm not necessarily, but usually it's because I'm not able to understand what you're saying. So I want to encourage you guys I don't want to discourage you from continuing to think about this stuff, but I want to encourage you to communicate more clearly. So I hope that doesn't discourage you. I hope that encourages you, and helps you communicate more clearly in the future.
Can I shortly explain my point in this
The
question?
point in the
Yeah,
give it a try.
I want to say you so that your presentation was good, and the idea that the time is only the change of things, that's very very in the core of the all theories. But when you have your densities and sparsers and so on, I want to give a hint about two sectors, for one for electrons and one for positrons, or because we have only so we have chosen the names for the minus and plus and so on. Okay.
We have certain names for positive and negative charge.
Yeah.
We've chosen names for positive and negative charge, and they're completely reversible. Is that what you're saying?
Yeah,
we could just decide to reverse them and nothing would change. Yeah, that's true. Yeah. Oh, is that that's what you're saying here? If that's what you're saying, I agree.
That's,
If you
all,
just
that's
change.
the only point. Yeah, that's the only point I
Okay.
want to say.
Oh, okay. Okay. Yeah, I agree. Yeah, this is actually, one of my goals, which has been put on hold for now, is to write an inductive proof of all of physics from the beginning. And that's been put on hold because I want to try and make some kind of progress in the short run in order to get more funding for the project as a whole. Because I think we might be able to make progress here in the short run, and then that will help us inductively systematize all of physics once more credibility is given to this approach of mine. But anyway, once that re-systematization is complete, there's going to be a couple things I want to change, and one of them is the polarization of charge. I definitely want the electron to be positive and the proton to be negative. And the reason, and a lot of people want this because when you have electric current, it looks like Jim already knows what I'm talking about. When you have oh, you don't? The reason for this, the reason this
No,
would
I'm
be a
just
good
thinking,
thing.
James,
Yeah.
good luck with that.
A lot of people want
That's my
this.
reaction.
Yeah, it would. You'd have to change a lot of things, unfortunately. But the reason this would be better is because when you have electric current, we keep track of the movement of positive charge. But then, much to our dismay, we found that it's the negative charge that actually moves through a body. It's the electrons that move through a body, and so the movement of the entities is opposite the movement of current, which is which causes certain things to be really confusing. So that it would clear up that issue if we just reversed what we called the charges. But yeah, good luck. That's right. Yeah, it would be very difficult to change like all the textbooks and everything. So okay, let me ask another one of Bruce's questions. Do synchronizing? I was a little unsure what you were asking here, Bruce. So help me. You can unmute and help me out as I talk through
Yeah,
this.
I realized I may have left something out, but go ahead.
Okay, so maybe you can fill it in here. You asked, do synchronizing metronomes do so by conditioning the medium? Yeah.
So it's distinct from the substrate. So if they're all sitting on the same substrate, sure, the motion influence can be communicated through the substrate. But if they're just in a vacuum, would they still synchronize? And would then the medium by which they do so be the ether, essentially?
Okay, so we have two, and by okay. So I'll read the question and I'll clean it up based on
Metronomes are physical.
what you
spring
just
loaded
anything
things.
that oscillates, as you're saying,
Yeah,
just any.
oscillators.
Okay, so when we synchronize oscillators, do we do so by conditioning the medium, or
when they automatically sync up, right? If you've ever seen a bunch of metronomes, they'll ultimately sync up. When they do so, what is the mechanism by which they coordinate their activities? Is that solely through the substrate, or is it through? Can it be through the medium if they're not sitting on the same substrate?
That's interesting, huh? Yeah, so if you have two oscillating objects that are somehow connected to one another and they have different frequencies, they'll push each other into having the same frequency. Right. Okay, is a phenomenon. So now is there a way to do that through the ether is basically what you're asking.
And I think I know the answer already. Like I realize radio antennas do this. So
do they really? Yeah, right. Yeah. So that's an example. So if you had two radio antennas, and I mean they communicate with one another through the ether. They're not mechanically vibrating each other. They're communicating with one another through the ether. But this makes me wonder about some things. Like this phenomena, it makes me wonder if this happens in other ether phenomena. I don't have any answers for you here, but you've brought up something very interesting. And the reason I think it's interesting is because, you know, if you have a bunch of electrons around an atom, for example, these are all, you know, oscillators that are quite close to one another in the same medium, the ether. And I wonder if they push each other into the same frequency somehow. And I wonder if, you know, bringing this effect in to understand what's going on in quantum phenomena. Again, I have no idea how it would connect, but it seems like that principle should apply. Mm-hmm. So it's one that's you've given me one more puzzle piece that might fit somewhere. So I appreciate that. Yeah.
I would want to see an experiment where two unconnected metronomes in outer space actually do synchronize with each other. I expect that they would not synchronize with each other.
Right.
Stands to reason.
Yeah. Like literal metronomes of things clicking. But the trouble with radio antennas is that they're driven. There's an actual like exterior force, so to speak, like continuing to make the oscillation happen. So it's not the same.
But so when I was young, we built a radio receiver. They had these little Heathkit type things, and it was passive, and it was receiving radio.
Mm-hmm.
It wasn't locally driven.
It had a diode in it.
Yeah.
Okay. It's still externally driven, which isn't the same thing as two oscillating things syncing up with one another.
Well, sort of. It
is sort of like that.
It is right. In this case, the diode receiver is the receiver of oscillating information from the transmitter, and it is adopting that oscillation in order to display it, for lack of a better term, locally.
Yeah. Right. Yeah. But I find this intriguing because there's all kinds of places where once you adopt an ether hypothesis, you start to wonder, like, well, wouldn't that effect happen, you know, in the electrons in an atom, for example? And in a lot of these quantum systems, it doesn't happen. There doesn't appear to be like a coupling between the electrons. But then there's a question of whether there's really just whether there's really two electrons in there. If it's all just one big wave, you know, if you have, let's say, you know, take a helium atom, it has two electrons buzzing around it. Is it really two electrons, or is it just that it's allowed to emit one wave and then a second wave, and then it has no electronness buzzing around it anymore? This is the and that would seem to make sense. That would seem to make sense of the fact that these systems don't necessarily couple to one another. They effectively, it's like the two separate electrons goes through one another. But maybe that's the case because they just really aren't two separate electrons.
Right. They're resonance.
In quantum mechanics, we think of it as that. Yeah. Okay. Okay. Well, so I've gone through all the questions that I wrote down. Now I'll open it up to the floor for any live questions. So just raise your hand physically or digitally, and I'll call on you at will. Go ahead, Matt.
What are your thoughts on our current system of units? That's kind of a thing for me. So just general thoughts and stuff for.
Let's see. System of units. I think we have a good system of units. One line of inquiry that I want to follow up on is the fact that the speed of light is lies at the heart of the definition of the meter. We define the meter in terms of the speed of light, and we don't know the one-way speed of light. So it makes me wonder. I haven't looked into this, but it seems like this is something that would introduce a bunch of flawed theories into our measurements themselves, it seems, because the presumption that the one-way speed of light is always the same is an unproven presumption. We don't know the one-way speed of light. Special relativity presumes that the one-way speed of light is the same as the two-way speed. And we don't know that. And so I wonder, and the meter, our unit of length, is based on the speed of light. So it makes me wonder if somehow this faulty premise has even infected our units. It's something I need to look into, though. I'm not sure if it does.
It's a really weird formulation. I mean, I actually went to the Wolfram Summer School just because I was so curious about this, did a small project on it. And when you go through the definitions, like you were saying, like the meter is defined by the speed of light. But the way that they do it, it's like they literally take the numerical value of the speed of light and they're literally solving for x, and then they put seconds on the outside. And seconds are defined by the hyperfine transition frequency of cesium-131. So then they line it up, and they do this for like the kilogram and everything like that, and they're going through, and like it seems to be pretty tight. It seems to work, but I'm just like, it seems like you said, it seems to work pretty well, and that seems kind of astonishing. But it's something that fascinates me.
Yeah.
Veritasium have a note on how there's an error baked into it based on the measurements of the Earth in establishing the length of the.
Oh yeah, because when we initially set up the meter, it was obviously the distance from the North Pole to the equator by root of Paris divided by 10 million, because obviously. Yeah. Which actually, like you said, because they were basing it on like a spherical thing there, but yes, there was an incremental error for that for like.
Yeah, and the guy who did the measurement screwed it up or something, and by some small amount.
That's one reason why I think we try and set them to the constants of nature, because even if you don't believe that's the optimal way to do it, still at least defined x is to y, yada yada, basic algebra. So
yeah, it's in general, I think using units that are set to constants of nature are really good, because the whole idea of units, I'm going to get pretty philosophical here. The whole idea of units is to make our grasp of the world objective, as opposed to subjective, as opposed to, and by objective is like, this is the way it is, as opposed to, this is the way that it seems to me. And now, why do units do this? Is because when you measure something, you're making a comparison between two things that exist in reality. You're not making a comparison between something out there and something within yourself. Like, oh, well, that sure seems like a big stick. So it's like, yeah, that gives you some gross kind of measurement. But if you have a way of comparing two objects within a certain level of accuracy, you really have grasped the nature of the object. And this is at the heart of Ayn Rand's theory of concepts. And this is why, and she maintains that measurement is at the heart of our conceptual faculty. At least it's at the heart of our conceptual faculty when we use it properly. And that kind of measurement is what makes it objective, is that you're grasping the world by comparing existence against one another instead of comparing it against something within yourself, something that you just said, oh, these objects are similar. How do you know? Well, I don't know. They just seem similar, man. Like that, and that's it's and the real archetype of this like subjectivity is Plato. At least he asserts his subjectivity. He says, oh, there are these particular forms in another dimension, and when things in reality look like those forms, what does it mean to look like those forms? There's nothing given on that. What does it mean? It's just apparent to you that they look like those forms. And that's the difference between, so I think, so measurement is very important. It lies at the heart of objectivity. Those are my thoughts on measurement and units.
Can I make some comments here?
Absolutely.
This thing that you just talked about with units is really about creating an agreement by which we can have additional conversation. So if we say meters, another guy says feet, and we're going to be really messing with each other every time we say anything.
I mean, that led to like a multi-million or billion-dollar accident on
Yeah.
Mars.
Yeah, the Mars
Exactly.
rover.
Yeah, I was thinking about that one, but I was especially thinking about the Ask Me Anything format of conversations. This is the first try that Inductica has tried, and it's gone pretty interesting. But we've had changes in the underlying model as part of the conversation. So Isa comes along and says, well, you know, let's put different names on things. Then you say, well, I really want to call the electron as a positive charge. And, you know, and time is just, you know, a way of things changing gives you time. But, you know, I don't think that way. There's waves, but I've studied compact disc audio in great detail. I actually wrote the CD-ROM file system for Windows 95. So I was the guy for compact disc at Microsoft back in the day, and then I helped architect DVD. So I've been steeped in this idea of digital audio and digital waveforms. So when I come back into the physics community trying to be a science explainer, people are talking about waves, but always in terms of natural waves happening in a medium. And now that we're thinking about the ether, there may be a digital kind of way of thinking about waves. It's a completely different way to construct waves and a different way of thinking about it. Going from vinyl to compact disc was a really major change. And, you know, even in this day of digital media, Demystify Psi just did an album and they're releasing it on vinyl. I'm like, wait a second, you know.
You can't do that.
Yeah, but they can. That's the thing, is in the conversation, there needs to be some constancy about what the conversation is about. So if you're going to bring in the river model, then keep the river model for that conversation and don't allow other models in that conflict with the river model. Stay with the river model. Or if you're not going to do that model, if you're going to do a different model, select that model up front. It's like choosing meters versus feet.
So what I'm hearing you
Otherwise,
say
it's very
is like,
confusing.
once you're saying like once you choose a standard and a context of viewing a problem, you need to stick to that, and that's part of what meters do. That's part of what units do, is that they keep you in that same measurement context the whole time.
For
That's-
that conversation.
For that,
And
yeah,
then you can switch
Yeah.
that at a
Yeah.
different conversation.
It's a frame.
yeah,
kinda.
right,
Yeah.
yeah. I would emphasize though that that's not the only benefit of units. Having
of
some
course.
specific. Having some specific way of comparing lengths against one another, that would be, you know, useful even if you are on a desert island. But it doesn't look like I'm receiving any blowback or any disagreement there. Okay, other questions.
I have
And
the
let's stick
question,
to Jim, go ahead.
James, I'm only familiar with the rudiments of physics. I'm basically an economist and a monetary theorist, but I struggle with the problem of definitions, and I want to ask you to what extent the problem of defining your terms in physics leads to misunderstanding and bad communication. It is a real huge problem in economics. I mean, I run into it and it's so frustrating because I guess I have to give an example. You know, the Fed defines inflation as an increase in the consumer price index.
Uh-huh.
That absolutely makes no sense. There's so many, because if a definition is the differentiation of the, if a definition differentiates the concept you're defining in its most fundamental sense, then mere price increases have nothing to do with fundamentality. I mean, it's just It's just nonsensical.
You
So,
you would conceptualize it as an expansion of the money supply, right?
yes, an increase in the
Yeah.
best definition, and I'm open to changes on this always, but the best definition I know of is an increase in the quantity of money caused by government action, which an almost equivalent definition is an increase in the quantity of an unproductive increase in the quantity of money.
So if they mined a bunch of gold one day, if suddenly we discovered a ton of gold and we had a gold standard, and then the price of everything in gold suddenly went way down. Oh wait, that would cause the price to go. No, that would cause the prices to go up.
Aluminum
It caused the
standard,
price to
for
go up.
example.
Yeah.
Yeah, because so
Aluminum
you
used to
wouldn't
be very,
define
very
that as
expensive.
inflation.
No, because resources. No, because resources would be dedicated to mining the gold and so forth. So it would be gold would be mined on the same. It would be produced on the same basis as anything else being produced. But so
I mean, it would just be a change in the relative value of different goods.
yeah, but right, and so prices can change, and increases in prices don't mean inflation. But prices can increase, and it doesn't have to be what we commonly think of as an inflationary experience. I mean, you can have a hurricane that causes prices to go up, and now you actually
Right.
have economists saying, "Oh yeah, hurricanes cause inflation." Well, that's nonsense. That's just nonsense. That makes the whole idea of inflation completely nonsensical and arbitrary. So
Yeah.
I don't want to get. I'm not trying to get stuck on a discussion of inflation. My point is that the problem of defining terms is a real issue, and people talk. It's not just that people talk past each other. People just don't even know what they're talking about. And
Yeah.
to what extent is this a problem in physics? I'm trying to determine if this is a problem that's mostly confined to the so-called social sciences, or if it's also a problem in all science or in all quests for knowledge.
This is a really great question, and there is a reason that I allowed us to go a little bit into the details of economics there, because I want to go into an epistemological aspect of all of this that I think is really important. First, to answer your question, though, it's not nearly as bad. Physics is the concepts in physics, and I'm going to focus on concepts here, not their definitions, and I'll get back to why later, but the concepts in physics are very tightly formulated. They're not perfect. You do sometimes get this kind of shenaniganry that you're talking about, where we have bad definitions, people talking past each other, stuff like that. But it's way rarer. It's way rarer, especially when you go back to the basics. Like the as far as I know, all the concepts around Newtonian mechanics are just beautiful. They're just perfect. They're people know exactly what they're talking about when they talk about mechanics. I think when you start getting into territories that are corrupted, like places where the ether gets rejected, you start getting people start saying things like the field contains energy. And that, that's a problem because the field isn't an entity. So how does it contain a thing? How does it have this property? What they really mean there is that the ether has energy, and that you can relate the quantity of energy that the ether has to the field that the ether has at that particular location. There's a legitimate mathematical relationship between energy and field. But there's this slight mistake there, but it ends up being important when you say that the field has energy or the field has momentum. You're attributing, a property that properly belongs to an entity. You're attributing it to a non-entity, a field, and a field is a capacity. It's not an entity. It's a kind of property. So we get these mistakes as we go further, but yeah, it's not nearly as bad.
This is
Now,
especially
well,
important.
hang on. Let's
sorry.
go back to either physical hand raising or digital hand raising, incidentally. But let's see. I'll call on you in a moment, Rick.
I raise my hand with mobile. There is no hand.
Oh,
Can I ask
Um,
my question about
Well,
the nature of the?
yeah. I'll call on both of you when I'm done because this is a very important epistemological point I want to talk about with Jim. So, let's see. So, let's see. Defining. So it's not about it's not primarily about definitions. So when you have a field with bad concepts or like people who are confused about the concepts, it's tough to get around that because someone might say a lot of people don't understand that concepts are human constructed. They don't understand that you're allowed to change the definition of a word. So they'll say, "Oh yeah, the hurricane caused inflation." And you'll say that's ridiculous. And they'll say, "What do you mean that's ridiculous? The prices went up. That's inflation." It's like saying like, you know, I got fatter and now my weight went up, and you say, "Oh, that's ridiculous. That's not what weight should mean." It's like, well, that's the way they probably look at you as though you had said something that ridiculous. So the question is like, well, our concept, like, is there a right way to conceptualize? And I think there is, and I detail that standard in my theory of induction, actually. I don't just give a standard, which I also give specific processes by which you can distill down all of the facts and come out with the right kind of conceptualization. And what is the right kind? Is when you meet this standard. The standard is you must form a non-contradictory identification of all the facts so far known. If there are facts out there that your conceptualization fails to capture, then you need to reconceptualize. You need to change the way that you use the words. And one of the main ways you can do that is by altering the definitions. The definitions are these levers that you can pull to change the way your mind uses the words. And so the definitions are not the same as the concepts, but they're very related, obviously. And if you change the definition, you change the way you use the word. And so I'm sure you have a really good reason for thinking that inflation should refer to, you know, this artificial expansion of the money supply, because I'm sure there's all kinds of facts that people miss when they think of it as just a mere increase in the consumer price index.
Correct. And I would just add, just to emphasize that price increases are actually one important, but not even the most important effect of an increase in the quantity of money. And so it is really wrong. It is really wrong to. It's like it would be like a doctor saying, "You have a fever, and that's the problem. Therefore, I'm going to throw you in an ice bath," yet without any understanding it might kill the patient without any understanding of what caused the fever. Was it cancer? Was it an infection? Was it, dehydration? What was it? So, in other words, it's actually lethal in understanding economics. And I don't want to. I want to hear you talk. I'm sorry.
Yeah. But this is good. I'm intentionally kind of letting you give me concretes here, because so what's happening here in economics is there isn't just when the government inflates the money supply, they're not just increasing the consumer price index. They're doing a bunch of other stuff that we need to keep track of too. And if you don't have a word for that, for the government increasing the money supply artificially, then you don't have a way of accounting for all of these other terrible downstream consequences of that effect. And it's the same as we have a word for fever, but we don't have a word for viral infection.
Correct.
And so you don't, and so now that isn't that big of a problem if you're just not aware of viruses yet, because the problem isn't your words. The problem is that you just haven't discovered the cause of the sickness yet. But imagine if you did know about viral infections, but you still insisted on calling it a fever. Then yeah, you might throw someone in an ice bath and effectively treat the symptoms without thinking, oh, how do we get rid of this virus? Bruce, real quick, and then I want to get to
it's to Issa, actually. I'm functioning as a proxy for Issa.
Oh, did he type in? He typed in the chat. I'm not watching the chat. Sorry, guys.
Right. He wants. He's ready
let's
to ask a question, and so he appears to be unmuted.
let's
but we don't
let's
hear him
take
now.
let's take Rick's comment or question real quick, and then we'll change to Isa.
When you're talking about the ether, you have the possibility of changing all the definitions of everything you already think you know, because the ether is happening at the really foundational kernel of all of the other things. So you may come, I've heard you say many times, well, we know this, we know that, we know this other thing because physics tells us this because we see these experiments. Now, I have to agree with all those experiments. I don't get to say that the experiment is wrong. But if I change the fundamental nature of all of the ether, and the ether is carrying all of the other things, then suddenly I get to, because I'm fashioning this ether out of whole cloth, right, philosophically, I get to redefine whatever I need to redefine in order to be consistent with the new theory. I can't stand, can't abide by previous ideas that are incommensurate with the new ideas that are coming in. And that was the whole idea of the structure of scientific revolutions, is as the revolution occurs, the ideas are incommensurate. So if you're going to have an Ask Me Anything, I can't bring up what I want to bring up during an Ask Me Anything. It has to be, I need to have a conversation about this new thing. And so that's actually kind of why I'm here, is to introduce that as a concept. Thank you.
Okay, well, we can get, I'm not clear on what you're trying to introduce. We can get back to that, but let's go to Isa. What was your question?
All right. My question is about the nature of the ether entity. Could its informative structure be qubits at all different speeds? I mean, normal matter has a speed, velocity fronts, but maybe the nature of the ether is, I say it's four-dimensional, so that there is all speeds, and so it's an informative structure better than rather than the matter structure. What do you think?
So, I didn't follow that. You're saying that maybe the ether is form, but it isn't matter? Is that what you're positing?
Yes. I think it's informative. It's a information structure.
Oh, it's
So that,
information. Well, what is okay? So it's okay. It's an
of course, the matter is
information
also
structure.
information, but
So yeah, it's not primarily matter, but it's information. What is information? Because when I think of when my concept of information involves a human being becoming informed of something. So like, and I don't think that's what you mean. You don't mean that like the universe is made of consciousness. I don't think that's what you mean. I'm guessing you mean information in the Shannon sense, right? That like Shannon information.
if you think about the temperature or this kind of entropy thing, there is a speeds, and it's a we know the temperature with matter, and so the material things. It's a normal way to think it, but maybe the ether is far beyond, so that there is information speeds up to the causality speed of the speed of light, and so and the local rest, and so I'm seeing it something exotic in the ether structure.
Well, I appreciate you trying to communicate your hypothesis here, but you know, as in your previous attempts, I don't understand. So, you know, keep working on trying to communicate it, and you know, and that'll help you hone the idea itself as well. Let's take a question from Adam, and then we'll get back to Rick so that he can clarify what he was saying earlier. Go ahead, Adam. He's working on unmuting.
There we
You
go.
can press and hold the space bar to unmute.
Sorry, my phone is like slightly disconnecting. So, James, hopefully if it disconnects.
Adam, you're unmuted and you're moving your mouth, but I still don't hear you.
Can you hear me now? Shoot.
See if you can see if you can fix that, Adam. While you're working on that, let's hear from Rick. Rick, try to you know, elaborate on what you were saying earlier.
I would love to. However, I think that it's very dangerous for me to do that.
Okay.
I've tried to introduce this conversation, and I've been really strongly rejected in strong forms before, and so I'm reticent. So I've worked on this since 2012 and found a discovery on November 21st, 2018. That's even before the pandemic, where I'm like, that's the answer that I've been looking for. That's what it is. And my gosh, how am I ever going to work this out? Because looking at the answer, I'm like, I don't even know how to do math on this. It breaks my whole idea of what I could do. And so I've worked on that for 7 years now, and I've worked through a whole bunch of problems, and it has survived every attempt for me to try to break it down. So I would like to bring this forward, and I especially want to publish it first to say, yeah, Rick thought of this, right? But what I'm finding is that there's so much entrenched stuff in the conversation that's already there that it makes the conversation very, very hard to start. Now, James, I see you exploring in the idea of ether, and I have some things to say about that, but I needed to not be part of an Ask Me Anything format where, you know...
Yeah. I mean, if you want to explore that...
And, yeah.
Yeah, I mean, an Ask Me Anything isn't. Yeah, that's not really the. I see. You're wanting to express your particular theory, and yeah, this isn't the forum for that.
Right, I can't do that. So
I see. Yeah.
like
Okay.
I say,
Well.
I'm
Okay.
reticent to even begin that. That
Yeah.
would be a mistake.
You should begin that in a different forum. This is Ask Me Anything. This is my forum.
Exactly.
Exactly.
That's
So-
part of that's why, you know, professional physicists will do an Ask Me Anything, because it shows off their talent. It focuses all the talent on the one person you're asking the expert, as if the expert knows. And the answer is you don't actually know. At the level of ether, you're exploring.
Yeah, I
And
mean,
asking
some of these things I know,
questions
some
and
of I don't know.
responses in that exploration. And this format doesn't allow that. It allows one person to shine really well.
I see. It's not. This isn't an exploratory format, is what you're saying. Yeah, I mean.
Correct.
So yeah, for that reason, I actually didn't answer quite a number of questions because I just didn't know. By the way, Bruce, I'm going to ask someone who knows the answer to your your one-way speed of light question, and then I will get back to you once I'm talking to him tomorrow because I don't know the answer. Bruce had this great idea for measuring the one-way speed of light, and I don't know why it does. I'm sure it doesn't work, but I don't know why it doesn't work. And so I need to ask a friend of mine who's really good at this stuff. They need to write a book. One of my students said they need to write a book titled A Bunch of Ways How Not to Measure the One-Way Speed of Light, because it would just contain so much physics in it. It would be very useful.
Yeah.
Now, I just realized that one of the questions I wanted to answer from Adam, I just forgot to answer it. So I'm just going to go to,
This is his gamma ray
what not
question.
to do. So
He mentioned the gamma ray question in the chat.
yes, I'm actually going to answer two questions. I'll do the gamma ray question first. Let's see. Let's look to the gamma ray question. Okay. What are your thoughts on the idea of a smallest fundamental size of the universe at the size of the smallest actually observed wavelengths of light, which is the gamma scale, instead of the more commonly suggested Planck scale? Now, I think I've heard, maybe it was you talking about this, which is that it's this claim. I don't know if it's true or not. I haven't verified this myself, but that there's a shortest wavelength that actually has been observed. And as a result, that's empirically an argument for maybe that being the smallest scale, the smallest possible scale. I don't have particular thoughts on this because I haven't gone into it. But I do want to address the idea that what a lot of people say, including Henry Lindner, who I've had on the show, he gave me a really good argument for why he thinks the ether is discrete. That is, the ether is not this continuous medium, but it's made out of discrete parts, each of a particular size. And like Adam is saying, maybe they're at this particular gamma ray scale. His argument was this. This was basically his argument. I added a little bit to it, but when I said this, he agreed. We were going back and forth, and so I formulated his argument the strongest way I could. For one piece of the ether to act on another, that piece has to have a particular identity. And it has to be distinct from the piece that's next to it. So that means the ether can't be continuous. It has to be discrete. It has to be composed of specific entities. It doesn't necessarily mean they're of some particular size each, but it means each of them needs its own identity in order to act on the next one. And obviously, to have an ether, you need each piece of the ether acting on each other piece of ether. So the idea is that there must be some particular finite number of these ether entities that constitute the universe. And I don't have an argument against that. I'm reticent to accept it. I'm very reticent about arguments like this because it's really easy to miss something. But I can't marshal anything against that argument. I had to tell him that. I have generally been of the opinion that we don't know if the ether is discrete or continuous. But that was a good argument. And so I have to acknowledge I don't have anything to say against that argument. That being said, I'm not sure how much that really matters at this stage because, speculations of this kind, they've always been of dubious value. So, for example, think of the Greeks. The atomists had a theory of atoms, and their argument was, if you cut something in half, and you cut the fourth in half, and you cut the eighth in half, you get blah, 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 blah. It has to stop somewhere, right? Why? Why can't you just keep cutting? I don't see why not. Now, whenever you cut, you would have cut a certain number of times. But I don't see why there isn't an unlimited potential for cutting. I don't see why that's illogical. So, I just don't see the argument. But even if we move that aside, what's interesting is when something very much like atoms came about, it wasn't what the Greeks were talking about. Chemical atoms, the atoms of, Lavoisier and, I don't think, rather the atoms of Dalton and Boltzmann, these are chemical atoms, and they are small bodies that are the smallest amount of a substance that can participate in a chemical reaction. That's my definition, by the way. They're small bodies, and we know that from the physics of gases. We know that they're small bodies, and we know that they're the smallest quantity of a substance that can participate in a chemical reaction. That's what's known about them. That is completely different from what the Greeks were talking about. The Greeks, Democritus and the other atomists, they were talking about the fundamental constituents of the universe, which we haven't found yet. So did we really gain anything from the atomists' conjecture here? Not in physics. I think in metaphysics this helped because it helped people see, like, it helped with the problem of change. People were asking, like, how is it that things have identity but also change at the same time? And the atomists had a poor man's answer, which is basically the parts don't change. It's just that they change their relationships with one another. Now, they didn't say that. They had this hypothesis about atoms, but it still paved the way for Aristotle's concept of form and matter, where you understand that, like, oh, the solution to the problem of changes is that you just don't have suddenly like a yo-yo poof, like turning into Hegel. You know, it's that all of the parts, if something changes, it's because the parts change their relation with respect to one another. No one of the parts just suddenly poof turns into something else for no reason. So these are some of my thoughts on you know, the possible discreteness or continuousness of the universe. And then finally, why I'm not sure if such speculations give us much in physics, because like we've been making, but I mean, maybe eventually they'd help, because eventually maybe we do get down to the fundamental level. So I don't want to, I actually don't want to dismiss it either, but we should be careful, and we should really ask, is this the most important thing to be using our time on? It looks like Adam has a comment.
If you have identity,
go ahead.
If you have identities in relation with each other, so that there is no difference, then you have no different identities. You have only one identity there. So you have one information qubit, and or the atom, you say.
So you're giving me a sense of what you mean by physical information.
I think Henry said this in this respect. What he said.
Oh, Henry mentioned. I didn't know Henry mentioned this, but yeah. This is in my understanding is like there's this understanding of information as physical, and I haven't studied it yet, but I think information is is not a good term, because it makes it sound like everything's made of like consciousness, or like, you know, it's a confusing conceptualization. But nonetheless, even though the word may not be well chosen, I'm open to the idea that there's really something there. You know, Adam Reed, who's an objectivist, who thinks about some of this, he explained information, like, he explained this concept of information to me as like the quantity of identity, like how much characteristicness is in something. That was my understanding of what I could be.
Yes, that's okay.
Yeah. It's so yeah. I'm not necessarily against a concept like that, but we shouldn't call it information. I understand, though, it's called that because it relates to Shannon's equation for information somehow. I haven't studied it, though.
No, information theory has its history.
Yeah. Okay, and I'll take Adam's second question, which I really wanted to answer this one, and I totally missed it in my list. What advice would you give to someone starting a formal education in physics while still trying to maintain an independent scientific mindset, untainted by mainstream academia and modern science? Well, first, what I would say is you don't need to worry about, I wouldn't worry about like, I'm a little uncomfortable with the language of like getting tainted, because it's not quite how it works. It's not like you just expose yourself to too much of the wrong ideas and then suddenly you become one of them. That's not, you probably didn't mean that, but it's important to just know that Bruce is doing the zombie thing. So, one of us. But yeah, it's important not to think of it that way. The important thing is, basically, here's the answer to your question. Before accepting any conclusions in physics, mathematics, make sure you understand all the observations and reasoning steps that prove that conclusion. Okay, now, while you're in a physics program, you will not receive that information. On certain things you might, but usually you're basically being asked to take it on faith. And the best thing you're ever going to get is some kind of equation, which you're supposed to take on faith, and then a deduction from that equation that proves the conclusion. And then you'll ask, where did you get the original equation? And sometimes the professor will give you a hard time and he won't answer the question immediately. He'll start getting frustrated with you. But once you get down to brass tacks, what he'll say is they'll say, look, they can't, and many professors have literally told me this over the years. Look, they came up with this equation. It happened to work. It happens to be consistent with the observations. Therefore, the things we deduced from it are also going to be consistent. And the things we deduced from it also ended up consistent with the observations. So we accept the framework. And that's their reason for, and that's the hypothetico-deductive method. So like there's a reason and I don't think that is a good way of doing it. So the main way to maintain your integrity is to not accept things that you don't understand the observations and reasoning steps for. Now, what's the proper way of understanding the observations and reasoning steps? Well, I've written an entire book on this, on how, like, what do you need to do to go from observations, reasoning steps to conclusions. So like, that's my theory of induction. I give a method of doing that. One way to understand how that has been done in practice is to watch my inductive summary of physics, which you can get if you're all of you are patrons, but for anyone watching, you can become a patron for just $5 a month and you can watch those inductions. And that gives you kind of a play-by-play, step-by-step sense of how it's been done in the past. How did they do observations and reasoning steps to prove these conclusions? And so those two things, the theory of induction, like giving you how it's done, and then the practice of induction, this inductive summary, which is a semi-history of how it was done. That is my suggestion on how you learn how to prove something to yourself. Okay, but all of this comes with a giant caveat, which I'll repeat. In your physics education, you're not going to get that. You're not going to get that. Okay, but does this mean you just don't do a physics education? No. Unfortunately, getting like a bachelor's in physics, going to a university, getting a bachelor's in physics, this is still the best way, in my opinion, to start your physics education. But unfortunately, it is only a start to your physics education. It is not enough on its own. It's a really, now, if you're some kind of autodidact who's just really good at studying on your own, you might be able to do better, yeah. But for most people, including, me when I was college age, I would not have been able to make it on my own. I needed the breadth of information that a college degree gives. I needed that breadth of information. Unfortunately, as far as I know, you can't get that breadth anywhere else. Unfortunately, the way you basically have to take in this information and maintain your epistemological integrity, what you have to do is you basically have to just treat it as an introduction to everything. Hey, they told me about the law of gravity. I have no idea how they proved it. I have no idea if it's even true. But hey, they told me about that. They told me about this. They told me about that. Yeah, quantum. This experiment disconnected from everything else. That equation disconnected from everything else. Okay, just pile it all in. It's like a Tarantino movie. You watch the whole thing. You have no idea what's going on. And then at the end, you think about it and you're like, oh, okay, like I get it. Then she went here and then, and then you get it at the end, basically. That's how, and the program is just an introduction. If you go through my inductive summary of physics, you're going to get a great sense of how it's all done, but I don't take you through the math. I don't give you math. I don't give you like problem sets. I don't give you work in the lab. I don't have a comprehensive physics education for you. It's a really good adjunct to put the pieces together after you, before or after you go through one of these programs. So hopefully that's helpful to you, Adam. All right, so are you in a physics program?
Can you guys hear me now?
Yes.
Okay. I'm having all kinds of technical difficulties, and I just switched from my phone to my computer. So I'm planning to start a physics degree in the spring. So I haven't started
Awesome.
yet, but I'm enrolling
Fantastic.
coming up. So I'm planning to try to do
Cool.
up to
Yeah.
a bachelor's degree in physics and a master's for electrical engineering specifically.
Wow. Well, that's quite an undertaking. Good luck with that, because that's
thank you.
quite a challenge.
Is it all right if I followed up on the
Bruce.
gamma ray thing real quick?
Yes.
So sorry, I was having so many issues. So the key point with the gamma ray thing is, the smallest wavelength that we know of is a gamma ray, and really, the idea of a Planck level and all this stuff, it's like 100 quadrillion times smaller and more energetic and stuff. And it's not really like based on anything we've ever really observed. It's just theoretically it can get smaller and smaller. But the thing is, if you go by what we actually know is really there, that size is the same scale as subatomic particles and quarks and electrons and stuff. It's the same scale. So if you tried to model out an ether cell to explain light and atoms and stuff, that's what I'm doing. If you just wanted to model what we know about, you would assume a smallest unit is the gamma unit, and that is a quark. It's the exact same size. And it simplifies so many things, and it solves so many problems with quantum gravity of these impossible energy levels and hierarchy problems and stuff. It just, all the unsolved problems in quantum gravity completely disappear if you don't assume that those scales exist. So that's what's like exciting to me about this concept is like maybe, at least for what we've observed so far, maybe that is, the unit that's the scale at which all this stuff is happening, at least for matter and light and force and charge and stuff. That's kind of the big idea behind it.
I see. Yeah. Okay. Yeah. I don't I don't have experience with this personally, so I can't reject or accept it. But something like this is definitely worth looking into if it's consistent with all of the observations. And so that does, lend itself towards, this is the kind of hypothesis to follow up on. But something that's worth noting, though, is that it still doesn't constitute the kind of speculation that the atomists were doing. Like, we're not necessarily, like, I'm noticing you're not saying, like, oh, well, you're not making an argument like Henry was, where you're saying, oh, well, there have to be these fundamental units because of this, because of what we know about the nature of things. Which I'm not saying that's a bad argument, but
that is how I came to the conclusion. The law of Parmenides. I got excited when I heard you mention Parmenides and the plenum. I was like, oh, somebody knows about Parmenides. If you take Parmenides and he says you have to have something, that means there has to be a unit. There can't be space in between. So you have to have a unit. And they have to move out of the way to have motion. So it's like you can deduce this from the law of Parmenides is my point. So I do kind of do both. I'm doing real observation, what do we really observe, but then also deducing from geometrical principles what has to be there. So it's kind of a combination.
I'm not opposed to that kind of reasoning. You just have to be real careful because it's so easy to miss one little bit of context that just, makes everything go to heck. And although one thing I have to mention, I don't know if I've ever mentioned this before, but Parmenides had this wacky argument for, it's a lot of what you said. Well, it's funny. It's a logical argument, at least it's logical sounding, that leads to a crazy conclusion. He says, like, there's no space between objects because there's no such thing as nothing. So everything's an object. So therefore, so motion must be an illusion because everything has to just be locked in place. There's nowhere to go.
Right.
There's nowhere, and so that of course sounds absurd, but something that's kind of funny to me is, I'm not saying he's right, but one thing that's kind of funny to think about is if you think about the ether hypothesis where it's not that there's the version of the ether hypothesis where it's not that there exists space and then the ether like moves through space, but you instead entertain the hypothesis that like the universe is the ether.
Yeah.
And when I entertain that hypothesis in honor of Parmenides, I call it not the ether but the plenum.
Yes.
If you entertain a plenum hypothesis in this way, Parmenides isn't wrong. Because things don't really move in the sense we think of it. Instead, what's happening is that there's a medium. The parts don't move because the concept of movement doesn't apply to them. And waves move through the medium.
Mm-hmm.
The waves change their position. And what does that mean? It means the waviness exists in other ether cells than they did before. So I found this kind of humorous because obviously I always just rejected Parmenides' argument because it like leads to an absurdity. But yeah. I can't help but wonder if at the time he said, yeah, I know, guys, it sounds crazy, but hear me out. Like, it's logical. It must somehow be true. Like, it must somehow be true. I don't know. I might be giving him too much credit. He was probably a rationalist and wasn't saying it this way. But I'd like to think that there was some insight here that's leading us, to the answers.
Yeah,
that's
way to
helping
go.
us here.
It's way to go.
It's what?
Yeah, it's really way to go. Thinking so that there is only object, no space between, or
Yeah.
all separations are defined by the entity.
Yeah. Yeah. And I do agree with that because there is no nothing. Nothing is not a thing.
Thank you, James.
So I saw a question from Bruce earlier, and then we'll go to Matt.
Okay, so it's actually, I'm referring to Jim's question in the chat. Jim was asking about your work on induction and wondering.
Well, go ahead, Jim.
Publication date, that kind of thing.
You've referred to your book, and I can't find it anywhere.
Oh, it's on Patreon. So what you do is you go to Patreon, and then you have to sponsor Inductica at $30 a month. And if you do that for just 1 month, then I'll give you the book. So Jim, I mean, you've already sponsored me for, I don't think it was at $30 a month, but like you've been sponsoring me for a while.
Sorry. Yeah. Okay.
Okay. Yeah. I'll just send you the book. If you want the book, I'll just send it to you. You've paid me enough. So yeah. You've already paid. Like some people, I just give them the book for they just give me $30 and then I email it to them. And I should mention the reason the book is in this form right now is that it's not the book it's complete, but it needs a lot of revision, so it's in an early stage, but it's perfectly readable and clear, but there's a lot of things I want to add to it, especially in light of Ron Pizzaturo's theory of induction that needs to be added to my book, and other things need to be improved, basically. So it's not in its final form yet. Matt.
Yeah, it just kind of reminded me of certain things of the past that seem to be like prevalent. Kind of like Lord Kelvin saying, it's like, well, perhaps these automata, these small atoms or whatever they may or may not be, are not at vortices in the ether. And that seemed to make a lot of sense. Fast forward, oh, that's a crazy idea. No, that's got to be totally wrong. And now I start hearing more and more folks, whether it's Stephen Wolfram, whether it's different experimentalists saying like, oh, okay, you could imagine these are like little, maybe like a knotted vortice and a medium or something. I'm like, okay.
Yeah.
Sorry, just remind me of that.
Yeah. It seems like it's something I need to think about. There are these, you might call them metaphysical speculations, although maybe they're not speculations, but people, the atom is asked this question like, well, how do you get change? Well, maybe everything's made of these small things and they don't really change, but they just change their relationships with one another. That would explain how change is possible. And, I've poo-pooed it a little bit here, but it probably helped a lot with chemistry. And I think in principle, this kind of reasoning where you reason from basic facts about existence, it is possible to come to conclusions like that with certainty. It's possible Henry's argument that the ether has to be these discrete units for the argument. It's possible he's right, and that's a. I'm not comfortable accepting it yet because it just seems like we still just might be missing something. But that's not a very good argument because I haven't explained anything I think he might be missing. So I just have to admit that that's where I'm at. So that kind of thinking, I think, it leads to real progress. We have a couple minutes left. Anyone want to ask one last question? Bruce.
All right. So I gave you an example of the shear thickening of cornstarch as a potential inspiration for Chantal Roth's work on trying to figure out the fundamentals of the ether. The property of cornstarch is you can dump a bunch of it in a pool, for example, and you can slip slowly into it, or you can actually run across the surface because it will, under the pounding of your feet, it will thicken enough to support you during your run. And it seemed like she's wrestling with this elastic solid theory of the ether, and then you were talking about the fluid model of the ether, and it seems like an analogy, a material like this would support analogies that would allow you to think of a transformable medium that actually can change.
Think of it both
modes.
ways.
Yeah.
I definitely took note of that when you wrote that question in. And so, this is something, it's like I said, I think, it's one more puzzle piece that might fit in somewhere. So thank you for that suggestion. Yeah.
That's all I got.
Well, and thank you for that last question. And thank you all guys so much for supporting me. And thank you for all your questions and comments. And this was really fun, and we should do it again.
You're here.
Thank
Thanks, James.
Thanks very much for doing it, James.
Thank you, James.
Really
Bye-bye.
interesting.
Thank
guys.
you.